Yeah. Hi, everyone. I'm Steve Vance. I'm from NASA's Jet Propulsion Laboratory. I'm happy to be here in this festive environment to share with you a little bit about Jupiter's moon Europa and NASA's plans. I'll do it. NASA's plans to explore Europa to investigate its potential for life. So this is a somewhat low-resolution image of Europa, and already at this resolution, it looks odd. What's going on here? It looks like a skillet that's been scratched and rusted. What you don't see are a lot of craters. So immediately you wonder what's going on here. We should think about Europa in the context of its environment. It's a moon of Jupiter, one of the 4 Galilean satellites. If we look at the other satellites, there's a lot going on these ones as well. We notice first of all the outer 2, Ganymede and Callisto, are much larger, icy. Outermost Callisto is pockmarked with craters. The Jupiter system is an environment of extremes. So Callisto, the most heavily cratered body in the solar system, one of the oldest bodies in the solar system. And Ganymede, the largest moon, the size of the planet Mercury. Now, Europa is somewhat smaller by comparison. Again, not a whole lot of cratering happening and these weird fractured features on the surface. Then innermost Io. We don't see any craters. Instead, we see a world pockmarked by volcanoes. In fact, Io is more volcanically active than our own planet. And so we have to ask why that is. Why is the innermost moon so volcanically active? That has to do with tidal flexing, a tidal interaction due to the orbital environment. The orbital exchange of momentum between these moons is an input of energy. And so that tells us that something interesting might be the cause of these features on Europa's surface. So we have to go and find out what's underneath the surface. So just for reference, Europa is about the size of our moon. So I like this as a view of just a contrast between our own moon and Europa. Again, quite different, quite a lot going on that we'd like to understand. So what we think is happening under the surface, we think that Europa's ice is quite thin, and this is the reason why there are very few craters on the surface. And in fact, the Galileo mission, which ended in the early 2000s, gave us compelling evidence for a subsurface liquid water ocean on Europa. That is a salty environment. And we now know there are many ocean worlds in the solar system, but I think of Europa as the flagship for ocean worlds in the solar system, largely because we think the global ocean of Europa could be the most Earth-like. That is, pressures at the bottom of Europa's ocean are similar to pressures at the deepest spots in Earth's ocean, at the Marianas Trench. And there's so much energy going into Europa. We think if only a portion of that tidal energy is going into the mantle on Europa, there could be hydrothermal systems that could support life in the absence of direct input of energy from the sun, just as hydrothermal systems on Earth also support life. So with Europa, we have this tiny world the size of our moon that paradoxically has potentially twice the liquid water of all of Earth's oceans, and potentially present-day conditions that could be amenable for life. So we should continue to search for evidence of past conditions for life on Mars, but I think we also have a responsibility to go and search for present potential conditions for life on Europa. So let me just walk you through a few of the compelling features on the surface of Europa in a little more detail. All of the images that I'm showing you are put together from Voyager spacecraft images collected in the 80s and Galileo images collected in the 90s. So again, you see these fractured features throughout the surface. You also see these pockmarks. We're not quite sure what those are. We have some ideas, though. So we have very few craters. We'd like to understand how much energy was deposited by those, when they were deposited, but we think they were all deposited within the last 100 million years or so. Linear fractures all over the surface of varying widths, large bands that may have formed all at once or gradually due to tidal flexure. But you see that at every fractal dimension, the surface is fractured. So you have overlaying of all these different fractures. And some of them are clearly bands with central features, almost as if fractures were opening periodically under the influence of the tides. So you can picture all of Europa flexing under the influence of its tidal interaction with Io. You also see regions where the surface is broken up entirely, where it looks like rafts have broken off and become jumbled, flipped over in some cases, potentially hinting at liquid water just beneath the surface. So we want to find out if that is indeed the case. How thick is the ice? How deep is the ocean? We also see places where the surface appears to have been smoothed out. So are those due to thermal anomalies? Are there places on Europa in the ice that are more active than others? And do those perhaps correspond to activity in the ocean underneath? These are all things we'd like to figure out. Here's a different kind of chaos feature. It's called the mitten feature. Potentially, it's a feature that has refrozen. So you can imagine liquid water just underneath the surface that refreezes and expands and pushes the material up. Another notable feature that was the most studied chaos feature during the Galileo days, this is called Connemara chaos. Interestingly, all of the features on Europa are named after regions in Wales. So Connemara is a region in North England. And it's easily located on the globe of Europa as being just below these linear fractures that form an X on the surface. And just above one of the few cratered features, Pwyll, P-W-Y-L-L, which is pronounced Pwyll. So you can see places where these rafts have broken off and rotated and still preserve the fracture features that were formed on the original ice before the chaos happened. So all of this indicates thin ice, perhaps as thin as 3 kilometers, perhaps as thick as 30, that is geologically active. So just for reference, here's one of the few high-resolution images of Connemara chaos. This is about 4 kilometers across, and here we are for reference. So this is about as good as it gets in terms of understanding Europa's surface based on the current data set. But you can imagine yourself there walking around and dying of the radiation at the surface. I don't recommend walking around on Europa. Another interesting aspect of Europa that has come to light in recent years is the potential observation of plumes. So these would be eruptions of material from the ice that would be indicative of near-surface fluids and gases. And this is limited evidence from Hubble observations of Europa. This is in the UV. So these are features in the ultraviolet of oxygen and hydrogen in the ratios that you would expect in terms of water. So the reason we see these is because if this is indeed a plume feature, the water that was ejected from the surface immediately dissociated into its constituent parts, and we're seeing the aurora from that plume. And so there's potential repeat observations of plumes at Europa, but if they're there, they are not continuous in the manner of the plumes of Saturn's moon Enceladus. So we want to go back and explore these plumes as a potential indicator of what's in Europa's ocean, and we have the possibility for doing that with our planned Europa Clipper mission. So with the Clipper, we hope to map the surface in detail to figure out what the different surface features mean and to understand Europa in the context of the Jupiter system, including the radiation environment that bombards Europa's surface. That radiation, in addition to breaking up water that's ejected from Europa, breaks apart water at the surface and leaves behind preferentially oxygen. Because Europa's ice is active, that oxygen can make its way into the ocean. And so that oxygen could be a food for life. This is one of the reasons we think Europa is one of the best places to look for life in the solar system. So I think I'm loading a movie now. So this is the Europa Clipper. This is our current design. This is a solar-powered spacecraft planned to launch in 2022 and to arrive at the Jupiter system in late 2025 and to orbit Jupiter and fly by Europa more than 42 times. And by flying by Europa multiple times, similar to Juno with its multiple close-in sweeps around Jupiter, to build up a map of Europa and to map the many features of Europa in detail over multiple wavelengths in the UV, the visible, the infrared, the thermal. So we'll be able to understand how Europa works. So here's a movie of an earlier design of the Clipper flying over Europa. So coming into view is a relaxed crater. You can see that there's no central feature. That's indicative of potentially warm ice underneath. It's an actual feature on Europa. And here's a potential plume on Europa. And here's the clipper flying through it. So we can imagine grabbing on to the dust particles and the gases that are coming out of the plume and measuring what's in those, and thereby potentially understanding the chemistry of the ocean in the inside of Europa. So let me take you through a day in the life of the clipper. This is taken from the E35 flyby. So it's the 35th flyby of Europa. So now we see the spacecraft. This is actually the tool that we use to plan our mission. And so here in the lower left, you can see the different instruments on the clipper. We have 2 mass spectrometer instruments, 2 magnetometer and plasma instruments, again, an imaging suite that I mentioned to you. So this is showing what the clipper would be doing prior to its flyby. You can see the altitude above Europa. See, we're rapidly approaching Europa. Still 500,000 kilometers or so from Europa. See what our speed is. You can see what the different instruments are doing up here. And for context, this is where the clipper is in the Jupiter system. And now Europa is coming into view. We also see Callisto and Ganymede in the distance. And there's Io. So during the downtime, the solar panels on the clipper will be charging the batteries. And the clipper will also be relaying data that it accumulates during the flybys. So right now it's checking in with the Earth. We have special antennas on the clipper so we can maintain line of sight communication with the Earth, so that we can feel the tug of Europa as we fly by. And that tug, the Doppler shift in the radio frequency of those radio waves sent back to Earth, tells us about the gravity field of Europa, and thus tells us what's the density structure. And it will ultimately reveal to us whether Europa has an iron core, and perhaps what the mantle of Europa is made of, and also how thick the ice is. So now we're coming around Jupiter. We're beginning to image Europa. You can see the instruments starting to scan from a distance to get global scans of Europa. And the main science happens within a few thousand kilometers of Europa. So I believe once we get down to 20,000 kilometers, the instruments will always be on. You can see the thermal instrument is already turned on. So we'll be doing a thermal map of Europa and looking for anomalous features. And by doing successive flybys, we can look for changes as well. So now we're going into high resolution mode. We're building up localized images. We're going to get down to features as small as 0.5 meter. So we could see a car on Europa if someone happened to have parked their car there. In addition, we have an ice-penetrating radar called Reason that when we get closest to Europa will turn on and will allow us to look into the ice. So we'll build up these bands looking into Europa's ice. We're flying by. This is it. So we have the potential to see directly down into the ocean, build up basically a tomograph of Europa. So we'll have 3-dimensional imaging of the ice. We do basically the same thing as we're exiting. Continue to build up this data set, sample Europa's atmosphere. And one of the instruments, the mass spectrometer instrument, has a cold trap, so it grabs onto material as it flies by Europa and concentrates that material, and waits till we get far away from Europa, and then analyzes it far away from Europa, where it's not influenced by Jupiter's radiation as much. So that was a day in the life of the clipper, and we're currently in phase B, and we plan to launch again in 2022, and we'll keep you posted on our progress on that. So thank you for listening.